Various methods and tools are involved in stellar age estimation, an attempt to identify within reasonable degrees of confidence what the age of a star is. These methods include stellar evolutionary models, membership in a given star cluster or system, fitting the star with the standard spectral and luminosity classification system, and the presence of a protoplanetary disk, among others. Nearly all of the methods of determining age require knowledge of the mass of the star, which can be known through various methods. No individual method can provide accurate results for all types of stars. As stars grow older, their luminosity increases at an appreciable rate. Given the mass of the star, one can use this rate of increase in luminosity in order to determine the age of the star. This method only works for calculating stellar age on the main sequence because in advanced evolutionary stages of the star, such as the red giant stage, the standard relationship for the determination of age no longer holds. However, when one can observe a red giant star with a known mass, one can calculate the main sequence lifetime, and thus the minimum age of star is known given that it is in an advanced stage of its evolution, as the star spends only about ones of its total lifetime as a red giant. This is an accurate method of determining age. Various properties of stars can also be used to determine their age. For example, the Eta Carinae system is emitting large quantities of gas and dust. These enormous outbursts can be used to infer that the star system is nearing the end of its life and will explode as a supernova within a relatively short period of astronomical time. Very large stars like VI Canis Majoris, one of the largest stars known, together with NML Cygni VX Sagittarii and Trumpler 27, all have radii larger than that of the average orbital radius of Jupiter in the solar system, thus showing that they are in extremely late evolutionary stages. Betelgeuse in particular is expected to die in a supernova explosion within the next million years, as well as the scenarios of supermassive stars violently casting off their outer layers before their deaths. Other examples can be found of the properties of stars which illustrate their age. For example, Cepheid variables have a characteristic pattern in their light curves, the rate of repetition of which is dependent on the luminosity of the star. Since Cepheid variables are a relatively short evolutionary stage in the life cycle of stars, and knowing the mass of the star allows for the star to be tracked in its evolutionary path, one can estimate the age of the Cepheid variable. Exceptional stellar properties which allow for an estimation of age are not confined to advanced evolutionary stages. When a roughly solar mass star exhibits T-Tauri variability, astronomers can locate the age of the star as being before the beginning of the main sequence phase of the star's life. Additionally, more massive pre-main sequence stars could be her bigger B stars. If a red dwarf star is emitting immense stellar flares and X-rays, the star can be calculated to be in an early stage of its main sequence lifetime, after which it will become less variable and become a stable membership in a star cluster or star system permits an assignment of rough ages to a large number of stars present within. When one can determine the age of stars through other methods, such as the ones listed above, one can identify the age of all of the bodies in a system. This is especially useful in clusters of stars which exhibit a large amount of variety in their stellar masses, evolutionary stages, and classification, while not entirely independent of the properties of the stars in the cluster system or other reasonably sized association of stars. An astronomer would only need a representative sample of stars to determine the age of the cluster rather than painstakingly finding the age of every star. Thank you for watching. Don't forget to please like and subscribe. If you have a topic you would like to suggest, leave a comment.